Address scope determines where an address is valid and reachable. If addressing tells the network who and where, scope tells it how far that where reaches. Think of scope like postal zones. Some addresses are street level. The mail carrier delivers only within your block. Others are citywide, national, or international. In networking, scopes define the boundaries that contain or limit reachability. At the most basic level, scope answers this question. From which places on the network can someone meaningfully reach this address? The answer depends on the address type, network configuration, and administrative policies. Common scopes include link local, subnet, site or organization, and global. Each scope has different routing and policy implications. How does address scope work in practice? Link local addresses are valid only on the local network segment, the immediate broadcast domain. They are used for neighbor discovery, auto-configuration, and local services. They are not forwarded by routers. Subnet, or local scope, covers the routed network inside a single subnet. Routers know how to forward to these addresses inside the routing domain. Site or organization scope includes addresses routable throughout a private network, such as a campus or corporate WAN. Global scope means the address is routable on the public internet. Protocols and network devices enforce these boundaries. Routers will not forward link local packets, firewalls may block site scope traffic from outside, and NAT, or address translation, hides internal scopes from the global internet. There are additional dimension scopes to be aware of. IPv6 defines explicit scope semantics, link local, unique local, roughly similar to IPv4 private, and global unicast. Multicast addresses carry scope values that control how far multicast traffic should travel, from link-only to site to global. Virtualization and multi-tenant environments introduce logical scopes too. VRFs, namespaces, and overlays create isolated address spaces where the same numeric address can be reused safely in different tenants or overlays without collision. Why does scope matter? Scope shapes reachability, security, and address reuse. If an address is scoped to the local link, exposing it beyond that scope is a misconfiguration or a security risk. Scopes let architects reuse private address ranges across many different networks without conflict because those scopes are intentionally isolated. Scopes also form the basis for policy. Access controls, routing decisions, and monitoring rules are often written with scope boundaries in mind. When scopes are blurred, for example through misapplied proxying, incorrect NAT, or oversized Layer 2 domains, you get surprising connectivity, policy bypass, or troubleshooting headaches. What are the key features of address scope you should understand? First, scope is hierarchical and contextual. An address's validity depends on the network context and the routing fabric in place. Second, scope is enforced by forwarding behavior. Routers, switches, and gateways determine whether traffic crosses a boundary. Third, scope can be logical or physical. Virtual overlays create per-tenant scopes independent of underlying physical links. Fourth, scope impacts naming and discovery. Local service discovery uses link local and multicast scopes intentionally to avoid leaking services outside their intended audience. Fifth, scope interacts with translation mechanisms. NAT collapses scopes by presenting many internal addresses under a single external address, while proxies or VPNs extend scope by bridging otherwise separate addressing zones. What are the practical implications for network behavior and operations? First, scope effect troubleshooting. When an address is not reachable, ask which scope you are in. Are you trying from the same link, the same subnet, the same site, or from the internet? Misunderstanding scope is a common cause of it works here but not there problems. Second, scope influences security design. Keep sensitive services in narrow scopes and avoid exposing them globally unless necessary. Use ACLs, VRFs, and firewall rules to enforce scope boundaries. Third, scope determines how freely you can reuse addresses. Private ranges and link local addresses enable immense address reuse across tools, labs, and tenants, but they require clear isolation to avoid conflicts. Fourth, scope shapes scaling. Very large Layer 2 domains that blur link local behavior can cause discovery storms and inefficiencies. Consider using routing or overlays to keep sensible scope boundaries. Finally, scope matters for migrations and cloud integration. Moving services between scopes from on-prem site to public cloud changes reachability, monitoring, and identity assumptions, and often requires redesign of access control and DNS. A few practical tips follow. Be explicit about scope in your network documentation. List which prefixes are local, site, or global, and how NAT or overlays alter those boundaries. Use link local addresses only for their intended purposes and avoid relying on them for persistent identity. Design your Layer 2 and routing domains to contain discovery traffic where it belongs. When using private or overlay addressing in multi-tenant environments, ensure orchestration and controllers maintain isolation so reuse does not collide. And finally, when troubleshooting, always check scope first. It will often point you to the simplest explanation. Address scope is invisible when it's correct and painfully obvious when it's wrong. Understanding scope makes reachability predictable, policy enforceable, and multi-tenant designs reliable. It's a simple idea with profound operational consequences, the rules that say where an address really matters. That is, address scope.